we want to talk about motion. But before we do, I want to go over some of the vocabulary that we've been using just to make sure everybody's on the same page. We use the term orthogonal a lot when it comes to vectors. Most people think of perpendicular. Here's a couple of lines that have a right angle between them. They are perpendicular, so therefore they are orthogonal. But here are two curves. You cannot measure an angle between curves, only an angle between things that are straight, like lines and planes. But if I consider the tangent lines to these curves at their point of intersection, if the tangent lines are perpendicular, then we say the curves are orthogonal. Perpendicular refers to right angles between things, so lines and planes. My wall and my ceiling are perpendicular, therefore orthogonal. I'm standing at a right angle to the floor, so I am orthogonal to the floor. But if I have a surface, a three-dimensional surface, I can't have any angles. So consider, I've got a basketball, and I have a line. And let's say the line passes through the center of the basketball, out of the basketball. Now, there's an infinite number of directions this line could point, but I want it pointing directly from the center. So I want to describe how I can have a line be orthogonal to the surface. So now consider a plane. Now, the plane can only touch the ball at exactly one point. And if at that same point my line is orthogonal or perpendicular to the plane, again, the line and the plane I can measure an angle. So if my line and my plane are orthogonal, then I have a situation here where I have a line that is orthogonal to a surface because it's orthogonal to the plane of that surface. So that's the difference between orthogonal and perpendicular. Perpendicular, again, has to do with right angles. Orthogonal is a little bit bigger. Right now we're dealing with vectors, but eventually we're going to be dealing with surfaces. With functions, we know the rules of derivatives are such that the derivative of a sum is the sum of the derivatives, and the derivative of a scalar multiple is a scalar multiple of the derivatives. Well, it turns out the same rules apply to vectors. If I want the derivative of a sum of vectors, it turns out to be the sum of the derivatives. If I want the derivative of a scalar multiple, it's the multiple of the derivative, but there's also a product rule associated with derivatives as well, and it follows the same rules as functions do. So the product rule saying the derivative of a product, it's the first dotted with the derivative of the second, plus the second dotted with the derivative of the first, but we'll keep them in the same order just to make it a little bit easier to read. And part of the reason we want to do that, even though order does not matter with dot product, it does matter with cross product. So the derivative of the cross product, in this case, will be the first, crossed with the derivative of the second, plus the derivative of the first, because order does matter in this case, crossed with the second. Now let's consider the following vector in 3 dimensions. The vector valued function x, y, t. If I want the derivative of this vector, now think about in a units sense. This vector represents position, so it can be thought of as distance. So the instantaneous rate of distance per time, well, that has to do with velocity. Well, it turns out this is the definition of the velocity vector. So the velocity vector would be the vector of first derivatives. Using the same reasoning, if I said, well, what's the second derivative of r, which is the first derivative of v, well, by definition, turns out that's the acceleration vector, which would be the vector of second derivatives. Now, a very important observation. If I wanted to know what is the length of the velocity vector. Now, remember, the velocity vector, it's magnitude in a direction, but the magnitude is actually called the speed. Now, generally speaking, when we're not talking about vectors, people use the terms velocity and speed interchangeably, but they're not exactly the same thing. The speed, by definition, is the length of the velocity vector. So the velocity vector is speed in a particular direction. So if I said, what's the length of v of t, we notice then it would be dx dt squared, dy dt squared, dz dt squared, all under the root. And we recognize this. That's the arc length parameter that we looked at before. That's ds dt. Now, it's no coincidence then that the speed and the arc length parameter turn out to be the same thing. This becomes very useful later on when we look at components of acceleration. Now let's do a simple example of manipulating our position vector. Given the following vector, I would like to find the velocity and the acceleration at time 0. So the way we do things is we do not put the t equals 0 in first and then take derivatives, because if we do that, then all of our answers will be the 0 vector. We take all of our derivatives first, and then at the end we want to evaluate. So we'll start with v of t. That would be 6t e to the t negative 2 sine 2t. And then we'll find a of t, which would be 6 e to the t negative 4 cosine 2t. Now let's go ahead and find v of 0, which would be 0, 1, 0. A of 0, which would be 6, 1, negative 4. Now, based on what we did before, you notice these vectors, none of these vectors are orthogonal because I do not have anything of constant length. That was a special case. In general, given r of t, finding v of t and a of t should not represent much of a challenge. We're going to work into much more depth later on these things. Now, the next video, we're going to talk about specific aspects of motion in space.